So let's continue thinking about this concept of work done on a gas or an ideal gas. So our definition of work from physics 1 is just the integral of the force over the distance. Let's, for simplicity, just think of displacements in the x direction. We get rid of the vectors because of the dot product, and we can think of this as some force in the x direction, and we're going from some value of x to some other value of x. And this quantity is what we saw looks like P dV. So let's think of the concept of force. So if the force is a constant, then we have that the work done with that constant force just becomes force times delta x, right? Because we're just integrating an x. So we have work equals F dx, and that just gives us F delta x. And so if we draw this on a diagram of force and displacement, and we go from, let's say we're doing x1 to x2, then and we start at x1 and we go to x2, and the force is always, let's say, F star, so we can pull it out of the integral because it's a constant. Then here's the F star. The force always has this value throughout this interval. And so this calculation is just this side times this side. So this side is the force, and this side is the displacement, F dx. And so we get an area in here. And the work done is just the area that I have outlined there. It's the area under this curve. And so, by analogy, if the pressure is constant and we're changing the volume, notice that if we don't change the volume, then it's equivalent to having no displacement, and that's equivalent to having no work. So the volume must change by analogy if we have work, if we want to have work. So if P is constant, then the work becomes, by analogy with this, I can pull P out of the integral and get a delta V. And so it's just the area under the curve in a diagram that looks like this, but for pressure and volume. And so if we think of some volume initial and some later volume, V final or V1 and V2, and we have a pressure that's always the same, like this, let's just make this V volume 1 and volume 2, then the work is just this quantity, which is just the area under the curve, as it is here. Okay, so that's very visual, but now we want to explore situations where the pressure is not constant, and so we can think of the force not constant. So if the force is not constant, then the work becomes, let's say we start with some value F naught and we go to some force value F1, and it looks like that. We can't pull the F under the out from under the integral sign because it's not a constant, but it's still true that the work is the area under the curve. So in the Fx plane, we are now imagining that we start with a value F naught and we end at a value F1. So, and we have some initial value of x and some final value, x1 and x2, just like we did here. But now we're getting there in some way that we can specify, going from here to there, so the force is increasing from F0 to F1. This doesn't change the fact that this is still the area under the curve. So it's that area there. But now I get this in a way that it's not just one side times the other side, right? And the same thing by analogy, if pressure is not constant, so if P not constant, then the work is going to be some P1 to some P2, P dV, and in the PV diagram, this is going to look like P1, P2, and say some V1 and V2 associated with P2, and so pressure is increasing as the volume decreases, because of course we know that PV equals nKT, so that we have to also obey the ideal gas law. And so we have that the work done in this case is the area under this curve. It's not just one side times the other side. So it looks like that.